In this video, we're deriving the moment of inertia formula for a thin rod rotating about its center. So we're told the mass of this rod is capital M, the length is capital L. You can see the rotation axis there through the center of the rod. And we're given a generous hint. We're asked to chop the rod into point masses, and we're reminded that the moment of inertia of a point mass is given by little mr squared, where little m is the mass of the point mass, and r is the distance from the rotation axis. So the first thing we need to do is get a picture of a little point mass contribution into the diagram. So there's a tiny point mass increment of this thin rod, and we're going to call the location of that x. That's a variable location. We can choose little point mass contributions all the way from the left end of the rod all the way to the right. So x has a minimum value of negative L/2 for a contribution all the way on the left end of the rod to a maximum value of positive L/2 all the way on the right end of the rod. Now we're going to call our point mass contribution little dm. It's an infinitesimal contribution to mass, that's why we put the d in front. Now the goal here is to express the moment of inertia contribution of dm to the entire moment of inertia of the rod, but we have to take a moment to talk about linear density. Linear density is the mass per unit length. It's normally given the Greek letter lambda, and I can just write it generically as mass divided by length for a one-dimensional object. Just to make it more clear what we're talking about, the units of linear density are kilograms per meter. So I hope that makes sense for a one-dimensional object like a thin rod or a chain or a rope. We can talk about how many kilograms it has for every meter of that one-dimensional object. And a useful calculation that you can do with linear density is to realize that you can get the mass of any length of this object by turning this equation around and writing that mass is linear density times length. And the whole reason I'm doing this is because I want to express dm in terms of the width of that little slice. The width of that little slice is dx. It's an infinitesimal increment of x. And all I have to do is take linear density times the length to get the mass of that little slice. So dm is going to be linear density multiplied by dx, so lambda dx. So we're finally ready to write down the moment of inertia contribution of this one little infinitesimal point mass located at a distance of x from the rotation axis. So the contribution to the total moment of inertia, we're going to call that di. And this is where we use our point mass formula. The moment of inertia of a point mass is just the size of that mass, that's dm here, multiplied by its distance from the rotation axis squared, that's x squared. We then use our linear density to rewrite dm as lambda dx. So I can rewrite this di as lambda x squared dx. Once we've managed to write the moment of inertia contribution entirely in terms of a single variable, we're ready to add these up by using integration. So we can say the total moment of inertia is the sum of all the moment of inertia contributions. That's what an integral does. It's a continuous sum. So we write integral of di. Then we plug in our expression for di in terms of x. So we have the integral of lambda x squared dx. And we can put our limits of integration in. So the lowest value of x, again, was negative L/2. The highest was positive L/2. But here it's convenient to realize that we're taking the integral of an even function on an interval symmetric about the origin. X squared is an even function. Our interval is symmetric. This allows us to do just half the integral and double the result. So I'm going to put a 2 out in front. I'm going to pull the lambda out while I'm at it. That's a constant linear density for this problem. And we replace our lower limit with 0. So we're just doing half the integral and doubling the result. So I have 2 lambda integral from 0 to L/2 of x squared dx. Now we just guess the antiderivative of x squared, which is 1/3 x cubed, just using the power rule there. So we get 2/3 lambda x cubed from 0 to L/2. And now we see the payoff for taking the advantage of the symmetry of this function to get a 0 in the lower limit. When we sub that in for x, we get 0. The only survivor is when we sub in the upper limit. So we replace x with L/2. That gives us L cubed over 8. And I end up with 2/3 lambda L cubed over 8. We can cancel a factor of 2 here, leaving me with a 12 in the denominator. So I end up with a 1/12 lambda L cubed. Now this is a common feature to all of these moment of inertia derivations. At the beginning, we had to write down the linear density so we could express dm in terms of dx. But we don't want that linear density surviving in our final answer. We want to replace it in terms of the dimensions of the object that we're looking at. So our linear density, because this rod is uniform, is just the total mass of it divided by the total length. And when we make that replacement, we get 1/12 m over L times L cubed. One of the L's cancels. And I end up with the familiar formula for the moment of inertia of a thin rod rotating about its center. That's 1/12 ml squared. And we're done. If you enjoyed this video or at least found it useful, check out another one by clicking one of the links on the left, or click the Zach's Lab logo on the right to explore dozens of physics and math playlists. As always, you can leave your questions, comments, and requests in the comments section below, and I'll get back to you within 24 hours. Thanks for watching Zach's Lab, and best of luck on your math and physics journey.